So, hi everyone, welcome to the Atto Fridays. This week's speaker is Dr. Vincent Wanie. He is a scientist at Deutsches Elektronen-Synchrotron DESY, Germany, with the Center for Free Electron Laser Science. He holds a BSc in chemistry from the Université de Sherbrooke, Canada, and a PhD in energy and material sciences from the Institut National de la Recherche Scientifique, Canada, where he worked on the development and application of ultra-fast high-power lasers. And he joined DESY in 2019 as a member of the Atto Science Group of the Photon Science Division. His research interests covered the development of novel laser-based technologies for ultrafast spectroscopy, with a focus on the design and control of emerging properties in asymmetric molecules and materials. And his ongoing work centers on the development of a new experimental setup for time-resolved studies of chiral recognition, supported by his recently awarded ERC starting grant, KEBAB, starting in 2026. So everyone, he's loaded and he's gonna look for people pretty soon to build his group. So congratulations. And we are looking forward to his talk. So the floor is yours. Feel free to take it. And we are all ears.
First of all, thank you for the introduction. It's a pleasure for me to participate today to this seminar series. And I want to thank also the team that is involved in behind the scene to make it happen. So the title today of my presentation would be Novel Light Sources for Ultrafast Spectroscopy. And I will start by introducing first the group. In Hamburg, I'm a scientist from the Atto Science Group, as Carla mentioned. This is led by Francesca Caligari. And we are about 20 people at various levels. So we have PhD students, postdoctoral researchers, and scientists. And we basically focus our efforts on light source development, but also on spectroscopy itself. So as you can see here at the bottom, we developed novel light source for ultraviolet pulses, for instance. We developed compact VUV light source as well, and new schemes for soft X-rays and XUV generation via harmonic generation. And today I will essentially focus on the left part here, few femtosecond UV light sources. The main objective, which basically we aim to work on in the context of the work I will present today, is the perturbative study of electron dynamics in neutral molecules. And here there are two important words. The first one is perturbative, in the sense that we don't want to distort the system under study. And the second word is neutral, because we want to photoexcite without ionization. And to put the challenge into context, typically when we do attosecond experiments using harmonic generation, we study ionized target. And this is because the attosecond pulse has photon energy that are way above the ionization potential of molecules. So if we send an XUV pump, we probe with an IR field, we have a perturbative approach, but we are studying ionized targets. Inversely, if one wants to study neutral target, we can think of using a strong field IR pump and then probing with an XUV probe. But in this case, we are distorting the target. We are in a non-perturbative regime. So what we want to do essentially is to create sufficient bandwidth as a pump pulse to have a high temporal resolution, but with photon energies which are below, let's say, 10 electron volt, which is essentially more or less the order for ionization energies in molecules. And this restricts us to a narrow spectral range on the electromagnetic spectrum, which you can see here, the vacuum ultraviolet or the ultraviolet. And therefore, there's a need to produce ultra-short few femtosecond light pulses in the UV spectral range. And as an example, I show here on the right, for example, if we create a coherent superposition of electronic states, if the energy separation between these states is on the order of 1 electron volt, the oscillations will require a time resolution that is better than 4 femtoseconds to be mapped properly. And one can relax these constrained by, for example, exciting Rydberg states where the energy separation between the states is lower. And in this case, we can basically loosen the restriction in terms of time resolution and look at dynamics on the order of 10 femtoseconds. So with this context, I decided to split the presentation into two parts. The first part will be more about the kind of light source we have developed in the past years for UV generation. One approach we use is based on the titanium sapphire laser technology. We have developed laser-written glass cells for UV generation. And the second approach uses ytterbium lasers, high repetition rate lasers, where we perform first a post-compression of the pulse duration, and then we seed hollow core fibers for producing UV pulses. So I will go over these two approaches, and then I will give one example of the first experiments we performed with a few femtosecond UV pulses, where we investigated essentially electron-driven dynamics in chiral molecules. So first, in the context of UV pulse generation, typically what was done in the past was to use crystals, or we still use crystals, but there are some limitations which I will describe now. Already in 2004, you can see here, I don't want to go into the details, but it was possible to achieve pulses on the order of 7 femtoseconds, as you can see here. And this was achieved with a relatively complex setup, so a non-collinear optical parametric amplifier. There are several optics, and the idea here was or the key point was to use a deformable mirror to really adjust the spectral phase that you can see here in order to have the best compression and shortest pulse duration. So you can see that when switching off the deformable mirror, there's a certain phase profile, but when the deformable mirror is activated, the spectral phase is flat, and we reach near Fourier limited pulse duration of 7.1 femtoseconds. There are other approaches that have been developed. I give another example here. It's for wavelength centered around 340 nanometers. Again, with a flat spectral phase, pulses have been produced at the sub 10 femtosecond level, as you can see here. So this is already very good, but if one wants to go beyond the sub 5 femtosecond limit, there are a few limitations in terms of dispersion properties. So we have limited phase matching conditions in crystals, for example. And as I've just shown, we need to very carefully manipulate the spectral phase in order to obtain short pulses. I put a table here just to show, for example, the group velocity dispersion of different noble gases compared to fused silica or beta barium borat. You can see that there are orders of magnitude difference in terms of dispersion. And from this table, one could think of, or can think of, using gases to really avoid dispersion. Now, as an example, if one think of a 3 femtosecond transform limited pulse, you can see that already 100 microns of fused silica can stretch such a pulse above 18 femtoseconds. So the idea here is really to move towards the gas phase as a nonlinear medium to produce ultra-short UV pulses. So back in 2019, we already demonstrated ultra-broadband UV light pulses spanning from about 210 nanometers to 340 nanometers. And this was produced using this laser-written glass cell that you can see here. We have a small channel in which we can propagate the laser. And in this channel, we inject high pressure of gas, so on the order of 5 to 7 bars, to perform a direct third harmonic generation of a titanium sapphire laser. So we convert the light from 800 nanometer to 260, more or less, nanometer via direct frequency tripling. And such glass cell can sustain essentially these high gas pressure and are highly resistant to the intensity of the impinging laser field. So it provides an extended bandwidth, but since we are using gases, the conversion efficiency is indeed lower than crystals. Therefore, we need to increase the amount of emitters and therefore use high pressures. which basically creates an engineering problems because when we do spectroscopic experiments, we want to work in high vacuum. So we had to basically develop a scheme to extract the residual gas after UV generation. And you can see here what we built as a first generation of differential pumping scheme. Here on the right, you can see the glass cell, and I put a red line to show where the laser passes. And this glass cell is embedded into a differential pumping unit made of 3 subchambers so that we can collect the outflowing gas after the UV generation. So these are connected. This is the top view essentially of our experimental chamber. You can see the cell in the center, and then we have a first differential pumping stage connected to a roots pump, and then a second stage on both sides, which collects a second amount of residual gas. And this allows us to reach, in the end, into our spectrometers for experiments level on the order of 10 to the minus 6, 10 to the minus 7 millibars in order to do our experiments. This setup works well, but was relatively bulky. So we worked on the second generation of glass cells, which you can see here. Essentially, we decided to embed the differential pumping units within the glass cell. So you can see these 4 rectangular components here are basically used to pump out the residual gas. In the center, we still have a channel, an injection for the gas, and then we send our laser for the third harmonic generation. So this is a much more compact setup and an easier, let's say, device to operate. And we compared basically how efficient this new cell is. What you can see here is, as a function of the gas pressure, the amount of UV pulse energy that we can achieve. The color coding corresponds to different gases. So you can see that in argon, we can reach about 100 nanojoule, which is what we could achieve with the previous generation of gas cell. And there's some saturation below 1 bar due to ionization. But when we work with neon, we can achieve much higher pulse energy near the microjoule level. So really around 3 to 4 bars, we are above 500 microjoule. So this is already an excellent improvement compared to what we had in the past, and we are working with this now. And to understand the generation process, we have performed some simulations. We used basically we solved the unidirectional pulse propagation equation, which you can see here, using the propagation solver Luna.jl. It was developed by Chris Brahms and John Travers at Heriot-Watt. First, on the left, you can see the same graph that I presented before, the energy scaling, but it is compared to the simulations. We can see that we can qualitatively reproduce the trends. And on the right, I show basically the spectral evolution as a function of the gas pressure. So on the x-axis, you have the wavelength, and on the y-axis, you have the pressure, both for argon and for neon. And in C and E, I took 2 cuts essentially to show what kind of spectra we can achieve, together with a comparison with the simulations. And in both cases, you can see that we can obtain spectra with a transform limit on the order of 2 femtoseconds. So we can really use this software essentially to understand which are the key elements that contributes to the spectral broadening of our UV pulses. And I didn't mention, but we take into account ionization, and here is a linear operator where that takes into account dispersion and absorption. So we can really understand well what's happening in our gas medium during the nonlinear process. So shortly, I show where we placed this device. This is our attosecond beamline. Basically, it is seeded with 4 femtosecond near-infrared pulses, and we split this beam in 3 arms. The first one here at the bottom is the UV cell that I just discussed. The top part is the attosecond arm. So this is where we produce high harmonic generation, where we generate our isolated attosecond pulses using polarization gating technique. And we can recombine these 2 pulses together for experiments. You see example of spectra here on the right. And the third arm is the infrared as it is, so that depending on the experiment, we can choose which of the pump or probe components we want to use. And you have some characteristics here. I simply want to mention that this is a tabletop source that is now available via laser for EU. So if these characteristics are interesting for some of your experiments, we are happy to collaborate and to discuss basically the performances of our setup. Next, I will discuss how we produced UV pulses, but this time using ytterbium laser technology and multi-pass cells. So the idea here is to try to improve, let's say, the statistics of experiment by taking advantage of the high repetition rate of ytterbium laser systems that can go up to the several hundreds of kilohertz to the megahertz. The main drawback for this laser system is that the gain bandwidth is not as large as for titanium sapphire. So typically the output pulse duration for this laser is on the order of few hundreds of femtoseconds. So there was a need there is a need to post-compress these pulses further if one wants to do experiments with high temporal resolution. And the idea here that is sketched is that one could take advantage of spectral broadening by combining basically linear dispersion effects. And what I show here on the top is basically what typically happens in a conventional hollow core fiber system. So typically when we fill an hollow core fiber with gas, we can produce cell phase modulation and extend the bandwidth of our pulses and then post-compress them afterwards. But as the pulse propagates to the fiber, there's dispersion, and at some point the pulse temporarily collapse, and there's no peak power to produce any more further spectral broadening. So if one instead can manipulate basically the surface modulation and the dispersion, one can preserve basically the temporal profile for longer and therefore produce larger, broader pulses. So on the top case is where we can manipulate essentially only the dispersion. And at the bottom, you can see that if we can manipulate both this SPM and the dispersion, we can reach much shorter pulses. And the way to do this is by using multi-pass cell technology. So what we do is that we have a chamber with two mirrors, and we bounce on the mirrors. We focus in the center, and the chamber is filled with gas. As you can see here, we use krypton. And the idea is to use to balance basically the positive dispersion that is induced by the gas medium, and to compensate it with dispersive mirrors. So here you can see, for example, mirrors with -30 femtosecond square of dispersion. And the idea is to, as I explained before, to preserve for as long as possible the temporal profile of our pulses for cell phase modulation. And I will show briefly what kind of results we achieve. Here in black, you can see the spectrum of the laser without entering the multi-pass cell. The pulse duration in this case is 150 femtosecond. And after 15 bounces using the configuration that you can see here on the right, we achieve basically the spectrum that is in blue, shaded blue, supporting a transform limit of 13 femtosecond. So we can really reach a factor 10 of compression, and by doing the temporal characterization, we obtain basically pulse durations on the order of 15 femtosecond. The results that I show here were achieved at 1 kilohertz repetition rate, but we also tested basically the same setup, same pulse energy, same conditions, but increasing the repetition rate up to 200 kilohertz, as you can see here. And what we see is that there's no noticeable changes. There's a slight reduction of the bandwidth when going to lower repetition rate. And we tested basically the system up to 50 kilohertz, where the pulse duration remained constant. We're still developing and characterizing the higher repetition rates. But the main results here is that we can achieve factor 10 in terms of pulse compression, so going from 150 femtosecond down to 15 femtosecond. The transmission is above 90%, and we can scale the average power between 250 milliwatt up to 250 watt of average power. We use these pulses to seed an hollow core fiber, but this time to produce UV visible light. And the way we do that is that we use the effect of resonant dispersive wave. So in this case, we use a fiber and we adjust basically the nonlinearities and the dispersion to create a soliton, which starts breaking at a certain distance along the fiber and emits a dispersive wave in the UV. And basically, we recently this is a summary basically of what we recently achieved in terms of results at different repetition rate. You can see on the right that by varying the pressure, we can easily tune basically the central wavelength in the UV spectral range between about 260 and 350 nanometers. So this is the overview of the light source that we are producing, the UV light source that we are producing in the Atto laboratories. And now I want to move to the spectroscopy part. I will show you one of the first experiments where we investigated electronic dynamics in chiral molecules. So first of all, I want to introduce basically the concept of chirality. So chirality is a geometric properties of matter. And at the molecular level, you can think of it as a molecule which has a left-hand version and a right-hand version. These molecules have more or less all the same physical properties, but when they interact with another chiral entity, the outcome depends on the relative endedness between the two units. And this has tremendous importance in many fields, which I summarized here. For example, for drugs synthesis, polymers, for materials. It has potential for several applications, such as spintronics, molecular motors. One can think of circularly polarized OLED. And for all of these reasons, there's a high demand in terms of characterization of chiral molecules, purification of chiral molecules, and it creates a market that is over several tens of billions per year. So there's a lot of research in this area. And one way to characterize chiral molecule is by using circular dichroism. One can measure the difference in absorption between left-handed circular polarization and right-handed circular polarization. I show here an example of what can be done for characterizing, for example, the secondary structure of chiral molecules or proteins. This works well when the sample is highly concentrated, so in the liquid phase. But it is not suitable for gas phase because it's an effect that depends on or that involves weak interaction of the magnetic component of light and therefore leads to very low signals. So one way to circumvent this for the gas phase is to exploit an effect that is called photoelectron circular dichroism. Because it is based purely on strong electric dipole interaction. And I show here the concept of PCD. So if you have a certain light helicity, let's say left-handed polarization, and you study chiral molecules which are left-handed, what happens upon ionization is that you will produce electrons with a preferential emission direction that is along the light propagation axis. And here I've shown it as this yellow shaded area. And if you can keep the same experimental conditions, but instead you study the opposite endedness, so in this case, R enantiomers, you would see that this angular distribution is flipped along the light propagation direction. So if one has an electron detector with angular resolution, it can use this effect to characterize the properties of chiral molecules. And well, this concept has been established back in 1976 and further developed over the years at synchrotron facilities. It is extremely powerful because it's highly sensitive to molecular properties. For example, one can distinguish between ionized molecular orbitals. It is sensitive to isomerism. And here on the right, I show an example of what happens in terms of angular distribution of photoelectrons. When you use the same molecule, but you perform a chemical substitution. So simply by changing the fluorine atoms by hydrogen, here you can see that the map you achieve is completely different. So there was a lot of work done in the characterization of chiral molecules using PCD, and it made it very appealing for time result experiments. So I will briefly go over what has been done so far in terms of time resolved experiment. The first one was carried out in 2016, so a bit less than 10 years ago, by the group at Celia in Bordeaux, France. And what they did is to study phension. They essentially pump with a 200 nanometer pulse the molecule, and then looked at the temporal evolution of the system by probing with a circularly polarized pulse. And in this kind of experiment, we always do the experiment once with left-handed polarization, and then once with the right-handed polarization, circular polarization. We take the subtraction to create this LCP minus RCP. These are the PCD images. And we can also compare them to the sum of these two images, which corresponds to the conventional photoelectron spectrum. And in this work, what they could show is essentially is that PCD could reveal more relaxation channels than the conventional photoelectron spectrum. For example, they could identify the intramolecular vibrational relaxation that occurs on the order of 400 femtoseconds, which could not be captured via a conventional photoelectron spectroscopy. So already there, it was a kind of proof of principle that PCD can bring additional information about a molecular target. There were some experiments also performed at free electron laser facility. I show here an example, again in phension. What you see here is that via two-photon excitation, one can excite the molecule to a 3s Rydberg state, and you can see what kind of density this creates. And what was done was time resolved experiment by probing near the carbon edge. And on the right, I show the main results from this work. You can see in gray, this is the photoelectron spectrum. And the two curves in black corresponds to the PCD that is shown here on the right axis for two different time delays. So TA, the dashed line, is minus 200 femtoseconds. So this is pump-free. And you can see that at positive delay, the PCD, especially at the vicinity here, E2, changes. And what the team there could show was that the PCD reduces due to the contribution of the photoexcited molecule. So here you, at time without pump, you have a PCD signal that originates only from unexcited molecule. And when you pump the system, there's a contribution of excited molecules with a positive PCD, which lower basically the signal that you see here. And another example, moving towards, let's say, increasing the time resolution for experiments was performed in Switzerland. There, what they did is to look at the photodissociation of a molecule, a chiral molecules which dissociate into a chiral radical. And they could follow over a few hundreds of femtoseconds the chiral response of the formation of these new chiral species. So in this context, essentially, what we wanted to do was to address faster dynamics. Essentially, can we use now time-resolved PCD for capturing electron-driven dynamics, again, in neutral molecules? And here's the experiment that we have performed. We have chosen as a sample methyl lactate, which you can see here on the right. The chiral center is circled in blue. And what we did here is to pump the system to Rydberg states, so via two-photon excitation using our broadband UV pulses. So we pump just below the ionization threshold. We let the dynamic evolve, and then we probe the system via PCD using a single photon, infrared photon that is circularly polarized. As a detection scheme, what we used was this spectrometer here, this double-sided spectrometer, which allows us to collect simultaneously ions, but also electrons. I show briefly here how it looks like in the lab. So the top part here is our molecular source. This sample is in the liquid phase, so we evaporate these molecules, and then we send them through skimmers, and we reach the interaction region that is here. And on the horizontal axis here is basically the ion and electron detection. So I will briefly discuss the parent ion dynamics, simply to show what kind of time resolution we can achieve. So the blue dots corresponds to the parent ion time evolution. And basically the signal can be fitted with this red curve. and decomposed into two components. So we have a resonant component with a certain lifetime and a non-resonant component here that you can see with a Gaussian shape. And this non-resonant component basically provides the instrument response function for the experiment of 2.9 femtoseconds. So this corresponds to the convolution between our pump and probe pulse, and you can see that this is extremely short and will allow us to identify the dynamics that I will present now. So then we looked at the electrons. What we use again is velocity map imaging. You can see an example of typical map we achieve here in momentum space. Most of the signal is elongated along the UV pump polarization direction, and the kinetic energy of the electron scales essentially with the radius here. And what you can see is that most of the signal corresponds to low kinetic energy electrons on the order of 1 electron volt. So this is for a single helicity. So let's say left-handed polarization. What we do is that we repeat the experiment for right-handed polarization, and then we change the delay, and we look at the differential maps. And what we obtain is the kind of dynamics you can see here, this very rich 2D photoelectron distribution, PCD images. And if you focus on the what's inside the white circle here, which corresponds to photoelectrons below 100 millieV, you can see that, for example, the color coding changes as a function of the time delay on a very fast time scale. So in less than 6 femtoseconds, you can see that we go from an excess of electrons to the left side of the detector to an excess of electrons to the right side of the detector at 11 femtoseconds. So essentially what we do with these maps to get quantitative results is that we fit this distribution with cylindrical harmonics using p-basics. You can see here that basically we have Legendre polynomials, and what we do is to look at the energy and time-dependent coefficient that goes in front of this coefficient, and essentially the PCD is described by the odd coefficients, while the photoelectron spectrum is described by the beta zero here. And what you can obtain by using such technique is basically the time evolution of each of your coefficients. So on the top row, I show basically the even coefficients, so beta 0, which is the total photoelectron yield, beta 2, beta 4, and the odd coefficients, which corresponds to the chiral response of the system, beta 1 and beta 3. And I will mainly discuss this lower row because quantitatively we can define what we call a multiphoton PECD, which integrates over the odd coefficients here and obtain this kind of map here on the right. And we separated this map into 3 distinct regions where we see different dynamics. And before moving to the next slide, I want to emphasize that most of the features that you see here actually are induced by the beta 1. So beta 1 is really the component here that dominates the dynamic that we are observing. So if we integrate the low kinetic energy regions between 25 millielectron volt and 100 millielectron volt, what you can see is that the PCD is pretty strong on the order of 10%. And that it actually reverses emission direction within about 10 femtoseconds. And if you compare instead the same delay axis, but for the beta 0, which corresponds to the total electron yield, you can see that these oscillations are barely visible. So this emphasizes basically how background free measurements such as PCD can help to highlight such features. So again, I show here the 3 regions that we defined. And in these kinds of experiments, it's always good to verify what we see in a specific enantiomer by repeating the experiment in the opposite handedness or opposite enantiomer. So you can see the comparison here. You can see that basically the features are mirrored with respect to 0 pretty well. For each of these kinetic energy regions. So this was confirming that the effect that we see is purely coming from the chiral response of the system. So from there, we had our results, and we started to think, what is the origin of these oscillations? First, we confirmed that there was no vibrational mode. Essentially, in this molecule that can lead to oscillations on this order of about 15 femtoseconds. And this was indeed the case, and we started to think about how electron dynamics could lead to such modulation. We started to perform calculations, and we did both the excitation step and the ionization step. What you can see here are basically the two photon absorption cross sections via two photon excitation using our UV pulses. And the Gaussian shaped corresponds to energetic windows where two states can basically lead to oscillations with a period that corresponds to the experimental oscillations. And basically, under each of these Gaussian shaped, the promotion of an electrons to the continuum leads to the same energy where there can be interferences for observing electronic coherences. So knowing that, I show here what we obtain when we then perform calculations for the probe step. So in green, you can see the results compared to the experiment in blue. We started the calculations at 10 femtoseconds, which corresponds to a region where we are sure that there's no overlap between the pump and the probe. And we obtained excellent agreement, basically, with the experiment. You can see it both in the time domain, in the frequency domain. This is on the top row for 250 electron volt of kinetic energy of photoelectrons. And at the bottom row, this is for 500 milli-electron volts. And especially for the top case, the excellent agreement could be interpreted as a coherent oscillation due to the beating of two specific states, so a 3D state here and a 4P state that are separated by about 300 milli-electron volts. And now if one looks, for example, at the probability density, indeed, we can see that this oscillates with alpha period of 7.2 femtoseconds. So this was already an exciting results, but we went further into the interpretation and we started to look at how does the current that is generated by this electronic motion evolves over time. And this is what you can see here. The probability current, you can think of a molecule. And if we look at a sphere around this molecule with a radius of about 10 atomic units, where there's Rydberg density, you can see that the current is actually pointing in clockwise for a certain amount of time. And later on, during the evolution of the dynamic, the current starts rotating anti-clockwise. And this was an extremely interesting result because with such modulation of the current, one could think of using a second pulse to interact with the system at precise time delay to try to manipulate basically the reactivity of the system. And I will try to go through basically the idea we had as a proposed experiment. If you think first of two molecules within your molecular ensemble that are oriented in different directions. One of them can have a current at a specific time that is co-rotating with the electric field of a probe pulse, for instance, an ionizing pulse, while the other one can have a current that is counter-rotating. And because of propensity rule, in the extreme case, one molecule can be ionized while the other is not. And this means that we have a way to selectively filter basically molecular orientation via ionization, exploiting such current. And now if one looks at the orientation of the molecules that have been ionized as a function of the time delay, which is basically the equation shown here, you can see that along this molecular axis, the orientation is modulated with the same periodicity as the electronic beatings that we observed. So what we can do with this is that if this ionization leads to dissociation, it also means that the fragments that are emitted will be emitted in different directions depending on when the probe pulse or the ionizing pulse is arriving. And the proposed experiment we had was to basically define an asymmetry parameter in space, where we look not at the electrons, but at the ions via velocity map imaging. And from calculations, we can expect essentially very strong modulations on the order of about 30 femtoseconds. And you can see that the fragment can be emitted backward as at around 12 femtoseconds and then forward 7 femtoseconds later. I just want to clarify that this observable is not the same as PCD. So it's a new observable that could be used to map electron dynamics and currents. And we have been working now since a few months on demonstrating this. I will show preliminary results. You can see on the left, basically, what comes out from the VMI image when we perform frequency analysis. We have one component that comes out at a frequency that corresponds to the oscillations we observed in our PCD experiment. And if one produce the Fourier filtered image, here I show only 2 delays. You can see that with respect to the center of the detector, we have a depletion of the signal and an increase of the signal on opposite side, and that flips over time. And it essentially shows that basically fragments are produced in a preferential way depending on the time delay. So essentially, this is very encouraging results in terms of demonstration of charge-directed reactivity, because we really use the currents that are produced to impact on the emission direction of the ions. As I said, it's very preliminary results, so we would like to repeat this experiment in the opposite enantiomer to see the opposite effect. This would basically confirm the quality of these results and the robustness of the results. And now I move to basically one point that might have been observed already in the audience, is the fact that the theory do not have oscillations which are damped, while for the experimental case, you can see that after about 40 femtoseconds, the PCD oscillation vanishes. And we started to try to understand basically how we could model this. Of course, for Rydberg states, the high density prevents us to do dynamic simulations. But what we could do is to launch molecular dynamics trajectories for the cationic state and see how this evolves, because it relates well to the Rydberg states from which the electrons are emitted. And we use Newtonics for this. You can see here on the right the ground state geometry of the neutral molecule, and we have about 43% of trajectories, which leads to a geometry that is almost identical. So it means that there's no nuclear motion happening much in this case. And you can see also that for the density, the HOMO hole density, over time, this remains relatively constant. So this helps for preserving electronic coherences. And in the other case, 49%, there's a dissociation happening, while you can see also that the HOMO hole density is evolving in time. What you can see here is all the Rydberg states, potential energy as a function of time. The main point here is that you can see that most of these states are rather parallel with respect to the red curves in both cases. So whether the molecule is moving or static, coherence can be preserved because these states evolve in a parallel way. So in one case, the reduced nuclear motion helps to preserve electronic coherences. The fact that the Rydberg states are parallel helps to preserve also these coherences. And so basically the source of the coherence that we observe in our experiment was attributed to internal conversion. So what you can see here over 44 femtoseconds is likely internal conversion, so population transfer to lower states. So this is the whole results we obtain. What is next essentially would be to answer the following question. Are we able to extend a molecular control to larger systems? This is because so far, most of the work that have investigated chiral molecules explored single isolated molecules, while the interaction of chiral molecules is an interesting phenomenon. It's called chiral recognitions. It leads to several properties. And the idea here would be to increase basically the complexity of the system and see how the chiral recognition evolved in time. And one example, among what I would like to study is essentially to see whether or not we could use electronic currents as current-sensitive forces on nuclei to impact on the selectivity of the interaction between chiral molecules. And as Carla mentioned briefly before, I recently received an ERC starting grant for investigating these kind of interactions. So the title is KEBAB. It is for key exploration of intermolecular bonding in chiral recognition using advanced laser light beams. It is depicted here. The idea is to look really in the time domain at these molecular handshake between chiral molecules using photoelectron circular dichroism mainly. And there will be upcoming positions. So see if this is a topic that you are interested in, feel free to reach out to me. So I will conclude here to leave some time for questions. So what I have shown to you is that ultra-short ultraviolet light pulses open an uncharted regime for time-resolved experiments, especially in neutral targets. I didn't discuss it in this talk, but we have made some other works. For example, we have applied these pulses to liquid jets to look at impulsive stimulated Raman scattering. We also did experiments in methyl iodide. There we looked at non-adiabatic dynamics triggered by UV radiation. And following that, in this talk, I've shown you more precisely that ultrafast chiroptical spectroscopy is actually rapidly expanding with the new generation of stable sources and also large-scale facilities such as free electron lasers, where circular polarization is becoming available. So this is an exciting, let's say, moment for this type of experiments. In this talk, I've shown you that PCD enables the real-time study of ultrafast electron dynamics, and that basically the helical currents that are driven by the electronic motion could be an important tool for the photochemical control of chiral molecules by exploiting what we call charge-directed reactivity. While here we could apply this concept of charge-directed reactivity, but also in an enantioselective way. So with that, I would like to simply acknowledge all the collaborators that have contributed to the work that I have presented today, as well as all the members from the CFEL Atto group. And thank you for your attention. I will be happy to answer questions.
So thank you so much. It was really an interesting talk. The questions, comments, do write in the Q&A tab or raise your hand, and we're gonna look at those. Very good. So hello, Klaus Hansen. Comment, no question. Beautiful talk. I would like to understand more of this. Good night from China.
Good night, and well, thank you.
Yeah, good afternoon from Europe, we can say. And Mohammed Mehad Hassan, hello, thanks for your nice talk. So lots of compliments. And if you would like to understand, do feel free to ask questions. I know in China it is quite late, but if you would like, we are all ears. No pressure, but we are all ears. And we have someone who raised the hand. Let me see. Okay, Charlie Fleischer, go ahead. Hello? Charlie, you are in principle, you can talk. We have released you to talk. I don't know.
Can you hear me now?
Absolutely, absolutely.
Great. So this is really a beautiful talk. I just wonder, would this be possible to let's say manipulate the rotational degrees of freedom of your molecules prior to looking at the PECD signal and really find the connection between the angular distribution, or maybe the molecules are aligned or oriented, pre-oriented in a specific direction, and see how the electrons are emerging from that. Or would it be even something that makes sense to do?
So typically, if one aligns the molecule, then the effect gets stronger. One advantage of PCD is that it survives averaging. So there are works that show that aligning strengthen the PCD signal. I mean, for sure, if the molecules are aligned, we could repeat this kind of experiment and see similar dynamics. I'm not sure if there would be a real advantage for this, but for other samples, for example, where the PCD signal is much lower, this could be a way of improving the signal to noise, for instance.
Okay, thank you.
And we have another question, Samane Ahmadinejad. Is it possible to access slides and papers?
The paper for sure will be, I mean, what I presented today was mostly published. So I think since the presentation will also be available online, it will be easily accessible. And again, the slides will be as well streamed or published, so everything will be there.
Yes, so we typically publish this on YouTube once we edit it and get the okay from the speaker. So the talk is going to be unlisted for a while, but once we have okay and okay, we typically publish the live streaming, which is happening right now. So the answer is yes. And if there's anything he would like to have removed, then we also obliged, but it will be there. We have many talks that people watch later on. And Vishnu Santosh Kumar, hi Vincent, it was a very interesting talk. Can you explain more about why you're using circularly polarized IR light to probe? What the advantages over UV?
So yeah, it's there are different schemes, let's say, to do these experiments, but what you need for sure is one of the poles to be circularly polarized. So in this scheme, we pumped with the UV with linear polarization, and the reason for that is that we are working on developing ultra short circular UV pulses, but this is quite challenging, and we don't have this yet. This will enable another class of experiments, but for the moment, what we did is to pump with the linear polarization in the UV and probe with the circularly polarized infrared field, because creating this circularly polarized infrared field is established. It's easy to do, and this is what we call PCD when we ionized the target with a circularly polarized field. Now, if one would have access to circularly polarized UV, this is something that is called excitation circular dichroism. There's actually a Nature Physics published about this kind of excitation scheme. You can create currents in the bound state and ionize with a linearly polarized field that can be an infrared, and you would also see a chiral signature there. So both schemes work, but it depends on what are the pulses you have available and how challenging it is to create the circular polarization for your pulses. So if you would go to longer pulse duration, smaller bandwidth, typically this is not a problem, and you could choose easily the scheme you prefer to use for your chiroptical experiment.
So is that fine? Would you like to follow up on the question?
Yeah, thank you, Vincent. It was a great answer.
Thank you. So it's good to see we are getting a lot of feedback and a lot of interesting questions from everywhere. So would anybody else like to ask anything? Feel free to raise your hand, write in the Q&A. And also, if you are a subscriber, do write in the live chat on YouTube, because we're monitoring it right now. So wherever you're joining from, good evening, good morning, good afternoon, because I know we have people from everywhere here today. We thank once more Dr. Wanie for this really nice talk. So take care, everyone. I'm ending the streaming now. I'm going to end the recording. So see you next week. We're having quite a few Atto Fridays talks now. And see you soon.